slope fields. So for some differential equations, it is difficult to solve them or impossible in some cases. So what we can do is generate a slope field, which gives us the slope at various points in the coordinate plane to get a visual of what the general solutions for that differential equation would be. So let's take an example. Say dy dx is equal to cosine x. Now this is a differential equation that is not difficult to solve, but I think knowing the solution and then drawing comparisons to our slope field, we'll see why the slope field is useful for equations that we are unable to solve. So how do we generate the slope field? You notice I have my coordinate plane set up in a bunch of blue dots. I'm going to put the slopes at those blue dots. We could put them at more locations, less locations. The more you have, the better the representation for the general solutions. But how do we make these computations? So what we're going to do is evaluate the differential equation at the coordinates, because the differential equation will give us the rate of change at that point. So say I want, what is the slope at 0, 0? If I plug in 0, 0 into my differential equation, I plug in 0 for x and 0 for y. This function is not dependent on y, so all I'm going to be doing is evaluating this differential equation at the x values of our coordinates. We're going to get 1. So when I go over to my slope field, what I'm going to do is draw a little tick mark or a little dash that has a slope of positive 1. And I would repeat this for every single point that I've marked off as a blue dot. So we'll do one more, and then I'll fill the whole thing in. So dy dx, let's say we're evaluating that at pi over 2, 1. So the coordinate pi over 2, 1. Again, this differential equation is only dependent on x. So when I plug in pi over 2, I get 0. So the slope at that point should be 0. So I create a dash through that coordinate plane, through that point on the coordinate plane that has a slope of 0. Again, we're going to repeat this. So I'll fill this out now. So here's the completed slope field. Now when you're filling this in, you would never be asked to fill in this many points, but for whatever point you're filling in, show the computation off to the side. That way, if your artistic ability is not that good, it's easy for a grader to tell what that dashed line slope represents by giving it a numeric value off to the side and showing the computation, showing what point you're plugging in to the differential equation and what the resulting slope is. So that's always a good idea rather than just doing all the computations in your head. That way someone knows what the slopes of those dashes are. Now, that slope field represents the general solutions to this differential equation. Now, the reason why we're using this differential equation is because we can find a solution, and then again, we can relate it to this graph to check to see that the slope field does in fact do that for us. So this is a separable differential equation. Integrate both sides. So we're solved for I. So here's our general solution. Now let's check out this graph. If we pick one coordinate, let's start at 0, 0, and we follow along the slope field. So imagine if we start at this point, imagine that is like a leaf on a river, and you're flowing along the river by following the rates of change or the slopes. Now, when I follow these points, that curve that I just graphed is a sine wave. This is a sine curve. Now, this is a specific solution. In fact, this is our particular solution through the point 0, 0. So we get y equals sine x. Now, we can trace many other curves. We'll use a different color. So what I'm tracing out is another particular solution. But all of these together represent a family of functions whose derivative is cosine x. And therefore, these purple sine waves together represent all of the general solutions to the differential equation. So the slope field, by tracing it out, following it along, we can identify a particular solution through a point. So you may be asked, draw a representation for the particular solution through the point pi 3. So pi 3, they give you that dot. Again, the way you do that, imagine you're flowing along some river by following the rates of change the slope field gives us at these points. So there's an example of a differential equation we could find a solution for, a slope field representation of that differential equation. And now we can see why, for solutions that cannot be found algebraically or using integration for our differential equations, we can at least get a visual representation of the solutions through the slope field. And we can identify particular solutions by tracing along the slope field through the given point that we want to find a particular solution through. So that's the idea behind slope fields. If you had a slope field or a differential equation that was also dependent on y, so in this case it was just dependent on x, but just to show you, if we had dy dx equals y cosine x instead, when we're evaluating at, say, the point pi 2, again, plug in pi for x and 2 for y. So 2 times cosine of pi equals -1 times 2 equals -2. So when I was doing them originally, there was no y value in the differential equation, but just to show you an example of one that would have one, when we evaluate at a point to get the slope at that point, plug in the x-coordinate and plug in the y-coordinate. So don't forget to plug in that y-coordinate. They're not always going to be solely dependent on x or y, sometimes both. And then again, once you find the slope, draw a dash mark that represents that slope, show your computations off to the side so there's no question about what that line represents. Slopes of 0, remember, are horizontal. If the slope is some number divided by 0, that slope is undefined, and you should have a vertical dash. So horizontal dash, slope equals 0. Vertical dash, slope undefined. And how's that going to happen? When you have a number over 0. So just be aware of that as well when generating your slope fields.